equation I'll put. I don't even know what I wanted there, but that's what I want today. In many real-life problems, however, functions are represented by a combination of equations, each corresponding to a part of the domain. Such functions are called piecewise functions. So we talked about piecewise functions a little bit when we were talking about absolute values. So now we're going to actually do like some cool-looking graphs. Okay, so before we do that, did you know you can evaluate a piecewise function? So, and this is actually key for what we're going to be doing in calculus next year, is if I have a piecewise function, it's saying the function's valid for when x plus 2 is valid when x is less than 2, and the other function, 2x plus 1, is valid when x is greater than or equal to 2. So, which equation would I plug 0 in if I wanted to find f of 0? Well, that would be less than 2, so that would be the first equation. Does everybody see that? So then it would be 0 plus 2 equals 2. Does everybody see how I'm doing this? Okay, what about when it equals 2? So f of 2. So if it equals 2, which equation am I using? The second one. So 2x plus 1. So it's going to be 2 times 2 plus 1, which is 5. We good? Okay, when it's 4, that would be where x is greater than 2. So I'm going to use the second one as well. So f of 4 would be 2 times 4 plus 1 is what? 8 plus 1 is 9. Good? Okay, so now graphing ones. Basically, there's a wall, or I don't know if we call it a wall, but things change at where x is 1. So do you see where if I just have something kind of going through here, I'm going to get rid of it. But this is where two different functions are actually happening. On the right of one, something's happening, and on the left of one, something's happening. So on the left of one, what's happening? Well, we have a line that's on the y-intercept of 1 and up 1 over 1. And normally we would draw a line that goes like this, right? Everybody understand? Don't do this in pen, though. Okay, so, but it's saying it's only valid when x is less than 1. So that means anything on the right here is not true. You see that? So now I'm going to get rid of this line because we don't actually need the line, but I want to show you. So everything up into that line was good. So how do I represent going as close to x equals 1 as possible without actually being it? Yeah, a circle not filled in. So right there, we're going to have a circle not filled in. So that represents me taking the line as close to x equals 1 as possible. And I know for sure it's at when y is 2, because if I sub x is 1 in there, 1 plus 1 is 2. You see that? Okay, so now, how would I graph negative x plus 3? Well, that's a point on 3 down 1 over 1. So if I'm just going to use a different color pen here, just so you can see what I'm going to erase in a second. So normally I'd put a point on 3, and I go down 1 over 1, and then I would make my line going like this. Does everybody see? Yes? But here's the thing. Again, remember that wall that was there on 1? Well, nothing, it's only valid, this equation is only valid when it's greater than or equal to 1. So now I'm going to get rid of this part of it. Now, the dilemma is, this actually is a filled-in circle, and this is a not filled-in circle. So what do you think happens there? Is it filled in or not filled in? It's not half filled in. Good try. You got to make a decision here. Some people like doing a bullseye. They go, oh, it's like this, and then it's like that. And then they go like that. No, that's not like that either. It's filled in. It's like what happens when you unfill a hole and then fill it up. It's filled up, right? So my whole entire function then is something that looks goofy like that. Okay, what do you think about that? Not too bad, eh? Okay, so now we have a parabola a constant function, and a line. And the walls are between -2 and 2. So I'm just going to put those walls there, just so I know that there's two different things happening. I'll erase them later. But does everybody see there's kind of three sections here, and three different things are happening. So when x is less than -2, it's a base parabola. Do you remember how to graph a base parabola? 0, 0, 1, 1, 2, 4. Yeah? Ring a bell? It looks like that. Yeah? Okay, so now what am I going to erase? Pretty much everything. Because it's only valid up until this wall. Does everybody see this? Now, is the circle filled in or not filled in? It's not filled in. Right there. Not filled in there. And if I didn't know what the height was, I would just sub in -2 and square it, and I get 4. So I know at -2 it's 4, but it's not really 4 because it's not equal to -2 there. Okay. Then what we have is a constant line between -2 and 2. So normally this constant line would be a line going through 3 through the whole thing, right? But it's only valid between the domain of -2 to 2. So that means I got to erase this. And you don't need to do it this way. I'm just trying to show you visually what's happening here. Is this function is only valid between here and here. So at -2, is the circle filled in? Yes. So I'm going to fill in the circle right here. Notice that they're not the same point. Okay? So I'm not going to fill in this because it doesn't connect, right? And then going to 2, is that filled in or not filled in? Not filled in. So I'm going to go all the way up to there and make a circle right there. Okay, we good so far? Okay, so now we have in the third region is a line that starts at a y-intercept of 1, up 1, over 1. So here's 1, up 1, over 1. Again, normally I would draw the whole thing, and maybe I will, just for fun. Because math is fun, right? Okay, so now I'm going to erase what I don't need. Did everybody see how I got this line? Point on 1, up 1, over 1. Okay, so now I'm going to erase because it's only valid when it's greater than or equal to 2. So now, oh, look at they connect there. So what happens there when they connect and I have something that looks like that? Yeah, we got to fill it in now. So this leads us to a calculus concept called continuous and not continuous. So if I were to say example 2 is continuous and example 3 is not continuous, can you come up with a definition of what's continuous and not continuous? Yeah. What? No? The best definition, and you're probably thinking this, if I were to draw this and take my pencil, continuous. How call it discontinuous at -2. Okay? Moving on. This is called a step function. It's kind of a cool function. It basically looks like steps when you're done. That's why it's called a step function. Okay, so it's saying it's a constant function 1 if x is between 0 and 1. So constant function is a horizontal line. So between 0 and 1, it would be, whoop, I can't even hit it at the right spot there. Let's try this again. It's going there. Does everybody see? And is it a circle filled in at 0? Is it not filled in at 1? So we gotta put a hole there. I'm a little off just because my pixels. Anyways, when it's between 1 and 2, it's a constant function 2. So now I step up. Do you see why it's looking like a step? Oh, that's off again. Right there. You see? And it's equal to 1. Right? And then it's not equal to 2. And then when you get to 3, between 2 and 3, it's a constant function 3. So it's like that. And it's the same thing. Filled in, not filled in. This is called a step function because it resembles a set of stairs. And you could go on. So this is another thing that you'll see in calculus. And it's called the greatest integer function. And it's denoted, it looks like square brackets, but it's got a double, it's like this. Has anybody ever seen this? Read some math textbook somewhere and saw that somewhere? Okay. So what it means is for every real number g of x is the greatest integer less than or equal to x. So if here's a good example of the step function, right? So if I said, what is the greatest integer of 2.1, where would 2.1 be on my step? It'd be right here, right? It would be right here. So what would it equal then? 3. You see? Where's 2.1 in my x? Right there. So it would be oh, that's 2. Sorry. That's 2. Sorry about that. It would equal 2. I said that totally wrong, didn't I? Okay, how about 1.9? 1.9. So it would be equal to 1. Does everybody see how this works? Do you know what I'm reading? Like I'm reading the height where it is. So what's another one? Let's see here. Let's do 4.3. So 1, 2, 3, 4. 4.3 is about there. So then it's say about there. What would that be? 4. It's the greatest integer less than or equal to that. Okay? So, write equations for the piecewise function whose graph is shown here. So, let's call it f of x. We don't know what it's called, but anyways. So it's equal to 2 different functions in 2 different domains. Where does the domain split up? At 0. So let's talk about where x is less than 0. Is it equal to 0? No. That's not filled in right there, right? Okay, so where it's less than, what's the equation of that line? X plus 2. So x plus 2, comma, where x is less than 0. Okay? We good? And what's the equation of this one here? It's equal to x where x is greater than or equal to 0. Yes? It's filled in there. Okay, so in calculus we have a formal definition for a function to be continuous. But if you can draw the function without lifting your pencil from the paper, then it's considered continuous. Okay, so example 5 says, in examples 1 to 4, which functions were continuous? So let's go back to example 1. Was example 1 continuous? Okay, so example 1, is that continuous? And if you can't see it visually, you'd have to see whether it actually connects. so you could graph it, but graphing it takes a long time. You know this is a line, and this is a line, but do they meet up? Or would they have to meet up at when x is 2? When x is 2 in this equation, you get 4. When x is 2 in this equation, you get 5. So it's not continuous. Okay? How about this one? Example 2, is that continuous? Example 2 is continuous. Example 3, is that continuous? No. Example 4, is that continuous? No. Example 5, is that continuous? No. So what was the only one that was continuous? Example 2 only. Yes? Okay.